So, like Eric said, one of the main takeaways here is to think about matrices primarily in terms of how they transform vectors, right? And we thought about how you could describe a matrix entirely by how it transforms basis vectors, right? And that uniquely determines the action that the matrix will have on any general vector due to the properties of it being a linear transformation. So for the exercises, it's really, going through the motions, seeing this play out, and hopefully getting some good visualization along the way. So I think I'll go over some of them here with everybody. And specifically, this will be helpful as we see how we build them in Python, because remember, at the end of the day, we are looking to use these mathematical tools in our Qiskit endeavors, right? So first, we saw NumPy introduced as a package yesterday, I think. And we can think of this as transforming just a list of a couple of elements. NumPy has the data type of an array, and that will behave very much like vectors. So first, let's just go ahead and initialize some kind of vector, right? Let's get ourselves a starting point. And let's think about what kind of transformations we can do. So as the code here implies, first we're going to think about this we're first going to think about reflections, right? And we'll see exactly how this is going to work. So in NumPy, we just have strings here or functions here that will perform the matrix multiplication, right, of a given matrix that we have conveniently named reflection matrix and our starting vector. And the rest of this code is really just to plot this in an illustrative way. So let's see what happens, right, when I perform this operation. Okay, so my starting vector in blue, -3, -1. So okay, if we take this as the x location, and this is the y location, we start down here, right? And so what this is telling me is that after multiplying by this matrix, right, which maybe is clearer if I write it like that, this is the matrix, to this vector, and you can check for yourself, maybe you can do it in your head, maybe you would have to write it out, that all this is doing is flipping the minus sign of my y element. And when we plot that out, it's pretty clearly, I could say in words that this is a transformation which flips the vector about this line, which happens to be the x-axis. Right, so that's a reflection as an operation encapsulated by this matrix. And we're starting to see how we can represent this as in Python by just using these data types and using the NumPy matrix multiplication function. Okay, good. So what about a more complicated transformation? For example, a rotation. Okay, so first we want to pick, obviously, the angle that we were going to rotate. And now we're going to get started building that rotation matrix, that rotation operation as a matrix, right? Maybe you could kind of see, you could kind of visualize if I wrote it in, on paper, this is the cosine of that angle, the sine of that angle, the sine of the cosine and sine of the negative angle, right? The details will affect the direction in which we rotate, but the point is that just by taking this function and putting them in this arrangement, as you can expect, what we're going to see is that my starting vector, right, after being acted on by the matrix that we've set up, is now rotated by 90 degrees, right? So this vector has acted on this matrix has acted on my input vector to, in this case, rotate so that I'm now in the positive x coordinate area with the same magnitude over here. And you could describe this however you want, but it's very useful to note that I can change that angle, right, however I want, and still see that, would you look at that, right? That I really am seeing that when I put this object, which we've talked about at length, and we just perform matrix operations or matrix multiplication, I can, you know, kind of concretely wrap my head around, okay, what I have done is I've given this transformation, right, an input, it has performed that transformation, and I can see that very clearly in the output. And so that's why this is this matrix with multiplication is equivalent to, hey, Fred, can you rotate my matrix by 60 degrees or something, right? So that is the transformation, the operation that acts on the vector, right? Okay. And so we have some of the examples that we've done together already in the presentation portion. We have some helpful recap material in these notebooks. For anyone who is brand new to this, I'm sure it felt very overwhelming, and I highly, highly recommend reviewing at your own pace. No need to be discouraged if this seems really abstract or just requires, you know, just give it time. Okay. And practice will help build that understanding. Okay. So yeah, so as we were getting to with those earlier plotting examples, right, we have code blocks that you can interact with to really play around with this and see, you know, make sure everything works. In this case, you know, this example code will add these two matrices. So when you edit them, it should be unsurprising that each element of the outcome is the element-wise, right, corresponding element sum of the input matrices. And we can also use the same or similar indexing rules for vectors and lists that we learned about during our Python tutorial sessions to snag the elements of matrices. It's just that this time I need to tell NumPy what both coordinates are of the entry that I'm interested in, right? Before, I only had one index that mattered, right? It was the order of elements in the list or the vector. And now, because I've laid it out in a grid, well, I have to tell it this many over and this many down. And so that's what this means, right? So I've got my matrix 3 over here. And if I want to say the 1, 2 element, you know, think for yourself, try to point out which element do you think it's going to return for just a moment. Remember that the first index is the row. And so the third entry, right, of the second row. So we're indexing, we're starting from 0, right? So the indexes are 0, 1, 2. And this means I go to row number 1, 0, 1. And this means I go to column number 2, which is 0, 1, 2. So we've got 14. And last but not least, we have an opportunity to see once again that matrix multiplication at work. Oh, vector 1, I think is defined elsewhere. But this is just a repeat of what we've seen so far. So yeah, so these are the exercises that I really wanted to drill in on together. Hopefully this makes a little bit more concrete our emphasis on matrices as entirely determined by how they transform vectors, right? Because this is really just, you know, we can print our rotation matrix and we'll see that it is just a collection of numbers, right? This is just a real matrix. But because of how we've set it up, it's very clearly equivalent to the transformation that we want it to be equivalent to, that rotation. Okay.